The latest scientific theories. How mathematics is surprisingly useful in understanding the universe. It is obvious that some things in our everyday world are simple and others complex. We know our sun will come up day after day exactly on time, but the weather changes in annoying and haphazard ways. Unless, like me, you live in Arizona, where it is almost always warm and sunny, so you can set your alarm clock the night before and be sure you will wake up at the right time of day. But if you choose your clothes ahead of time, you might get it very wrong. Those things that are simpler, look regular, and dependable can be described by numbers, like the number of hours in a day or the number of days in a year. We can also use numbers to describe complicated things like the weather, such as the highest temperature every day. But in that case, it's often hard to spot any patterns in the numbers. Our ancestors noticed many patterns in nature, not just day and night, but the season, the movement of the moon, stars, and planets in the sky, and the rise and falls of the tides. Sometimes they use sometimes they use the numbers to describe the patterns. Sometimes they use sound or poetry instead. Many ancient peoples went to a lot of effort with numbers and patterns to describe the movement of heavenly bodies. They like to predict eclipses, scary but exciting events where the moon blots out the light of the sun and you can see the stars in the very daytime. Knowing when an eclipse would happen required lots of boring calculation, and they didn't always get it right. But when they did, people were impressed. Long ago, nobody knew why numbers and simple patterns occur so often in nature, but about 400 years ago, some people began to study the patterns more carefully, especially in Europe. There were beautiful and quiet, skillfully made instruments to help observe and measure things accurately. People had clocks and sundials and all sorts of metal gadgets for distances and angles and times. Eventually, they had small telescopes too. These serious people called themselves natural philosophers and were that what we would now call scientists. One thing natural philosophers puzzled over was motion. At first, there seemed to be two sorts, stars and planets moving in the sky, and objects moving around on Earth. Everybody knows that when you throw a ball it travels in a curved path and it doesn't take many tries to see that the curve is always the same if the ball is thrown at the same speed and angles. Of course, our ancestors were well aware that the moving object followed simple, predictable paths. They knew it because their lives depended on it. Hunters needed to be sure that when a stone left a sling or an arrow left a bow, it would behave the same way today as it did yesterday. In Australia, The ancient people known as Aboriginals were so ingenious they could make a flat stick called a boomerang, and when it was thrown it would follow a special path that would cause it to curve back toward the thrower. By the 16th century, mathematics had gone some way beyond the simple arithmetic to include algebra and other fancy methods, and the natural philosophers were able to write down equations to describe many of the patterns found in nature. In particular, they could write equations to describe curves like a path of arrows and balls. For example, a simple equation describes a circle. A slightly different one, a squashed circle called an ellipse, and yet another describes the curve of a rope hanging between two poles. Using this more advanced mathematics, a huge variety of patterns and shapes could be described not just in words, but in symbols and equations right on paper and printed for other scientists and mathematicians to study. Useful thought all this was, it was still just a description of patterns in nature, not an explanation. The big breakthrough began with the work of Galileo Galilei in Italy in the early 17th century. Everybody knows that when an object is dropped from a height, it rushes toward the ground faster and faster. Galileo wanted to make the precise. How much faster does it go after 1 second, 2 seconds, 3 seconds? Was there a pattern? He found the answer by experimenting. He tried to dropping things and timing them. He rolled walls down slopes so everything happened more slowly and easily. Then he sat down with all measurement and did some arithmetic and algebra until he found a single formula that correctly describes the way that all falling bodies oscillate. That is, go faster and faster as they fall. Galileo's formula is very simple. If the object is dropped from rest, its speed increases in proportion to the time it has been falling. This means that when the object has been falling for 2 seconds, it's going exactly twice as fast as it was at 1 second. And there's more. If the object is thrown by from an high at an angle instead of just dropped, it will still fall in the same way, but it will also move horizontally. And Galileo's formula says that the shape of the path the object follows is a parabola. One of the curves mathematicians already knew about from studying geometry. The same steps came when Isaac Newton in England worked out how objects like balls change their motion, that is, accelerate or decelerate, when they are pushed or pulling by forces. He wrote down a very simple equation to describe it. In the case of Galileo's falling object, the force concerned is, of course, gravity. We feel the force of gravity all the time. Newton suggests that the earth pulls everything downward toward its center, with a force proportional to the amount of matter the object contains, known as mass. Newton's equation connecting force and acceleration then explained Galileo's formula for falling bodies. But this was just the start. Newton also suggested that not just the Earth, but every object in the universe, including the sun, moon, planets, stars, and even people, pull on every other object with a force of gravity that gets weaker with distance in a physics way called an inverse square. That's a fancy way of saying that at twice the distance from the center of the Earth or the Sun or the Moon. The force is 1/4 is strong. At 3 times the distance it is 1/9, and so on. Using this formula plus his equation for how from and acceleration are related, Newton was able to do some cool mathematics, some of which he invented, to work out how planets and comets move around the sun. Pulled by the sun's gravity, he also calculated how the moon goes around the sun, and the numbers all came out right. More than that, the shapes of the orbit were also correctly described by his calculation. For example, astronomers had measured that the orbits of the planets are ellipses, and the great Newton showed that should be from his calculation. No wonder everybody thought he was a hero and a genius. The government was so pleased they put him in charge of printing all England's money. The really important things about Newton's work on motion and gravitation is deeper. However, he proposed that his formula for gravity and his equation for force and acceleration were laws of nature. That is, they should be the same everywhere in the universe at all times, and can be never change. Rather like God whom Newton believed in. Before Newton, some people thought the motions of objects on Earth, like balls and boats and birds, had nothing to do with the motions of bodies in the sky, like the moon and planets. Now we knew that they all obeyed the sun laws. While other scientists had described smooth motion, Newton explained it in terms of mathematical laws. In practical terms, this was a huge leap forward, because now anyone could sit in a chair and work out how such and such as an object would move without ever seeing it or even leaving the room. For example, you can calculate where a cannonball will land if it is fired at a certain speed and angle. You can work out how fast it would need to go to fly off the earth and never come back. Using Newton's simple equation, engineers can figure out exactly how to point a rocket to send a spacecraft to a moon or Mars before they even have the money to build the rocket. All this made physics, the study of the basic laws of the universe, a predictive science. Scientists could play with their equation and predict things that nobody knew before, like the extent of unknown planets. Uranus and Neptune were found after astronomers used Newton's laws to work out where in the sky they should be, and we know you use those laws to predict the extent of planets going around other stars. Very soon, scientists began applying the same ideas to other forces, like electricity and magnetism. And sure enough, they were found to obey simple mathematical laws too. Then atoms and their nuclei were studied, and they also can be explained in detail with the mathematics formulas. So there are not quite a number of equations in physics scientist textbooks. Some scientists wonder whether it will go on like this forever, or whether all the laws and equations can be merged in some way into some super duper law that contains all the other. Quite a lot of smart people have peered at the equation to look for links, and a few have been found that turned out to be light. A famous example was that when James Clerk Maxwell, a Scottish physicist in the 19th century, found that laws of electricity and magnetism could be joined, and when he had done that, he solved the equation and discovered that the convent magnetic force could generate waves of electromagnetism. When he worked out the speed of the waves from his equation, he found it was the same as the speed of light. Bingo! Light must be an electromagnetic wave, he said. The quest for a super duper law convening all the force goes on. It needed a really bold youngsters to put everything together. When I was a schoolboy, I liked a pretty girl called Lindsay. One day, I was doing a homework problem in pixels. I had to calculate, that is, predict one angle to throw a ball for it to go to the maximum the distance of a hill of a curtain sloth. Lindsay, who was studying library arts, sat opposite me in the school library, which was nice, although it made me a little nervous. She asked what I was doing. Mm, And when I described the problem, she remarked in wonderment, "But how can you find out what a ball will do by writing this on a piece of paper?" At the time, I thought this was a silly question. After all, this was my homework. But Lindsay had actually touched on a very deep issue. Why can we use the simple mathematical laws to describe and even predict things that go on in the world around us? Where do the laws come from? That is, why does nature have laws at all? And even if for some reason there have to be laws of nature, why are they so simple, like the inverse square law of gravity? We can imagine a universe with mathematical laws that are so subtle and complicated that even the brainiest human mathematicals would be baffled. Nobody knows why the universe can be explained with the simple mathematics, or why people's brains are good enough to work it all out. Maybe we just got lucky. Some people think that is a mathematician God who made the universe that way. Scientists are not very interested in ghosts. Thought could it be that life will arise only if the universe has simple mathematical laws? So nature has to be mathematical, or we wouldn't be here arguing about it. Perhaps there are many universes, each with laws different from our own, and maybe some with no laws to speak at all. These other universes may be devoid of scientists and mathematicians, or maybe not. To be honest, it's all a mystery, and most scientists think it's not part of their job to worry about it. They just take the mathematical laws of nature as a fact and get on with their calculation. I'm not one of them. I lie awake at night, turning it all over in my mind. I'd like an answer, but whether or not there is a reason for the mathematical simplicity of the universe. It's clear that physics and mathematics are definitely interwoven, and that we will always need people who can do experiments and people who can do mathematics, and they had been better kept talking to each other, Paul.